Today, we're continuing on with these special topics. And this stuff, it kind of flows better than I anticipated it doing. Tomorrow will be a little bit more hodgepodge with this. But we start with a mixture. And we get into two unique types of ways that we can separate a mixture that we really don't talk about, okay? The first thing is not even listed on here. So a mixture, in this case that we're going to talk about, is a liquid mixture, all right? Both things are a liquid. If we had a mixture that contained different states of matter, let's say liquid and solid, water and sand, does anybody know the lab technique that you would use to separate those things out? Filtration. All right, too easy. All right, check. You know that. Now, this stuff is all a liquid. So, like coffee on the table, right? It's composed of cream and coffee and ice and things like that. That's all mixed together. It's all liquid mixture, all right? So, it would be difficult to separate that out via filtration, all right? So, category one, or method one that we use to separate it out, is chromatography. Chromatography is going to separate out, says due to attractive forces, aka what type of bonding? Is it polar? Is it non-polar? And then it also involves the type of solvent, the stuff that's essentially sucking up that particular solution. Hello? Yeah, you're going to create the QR code from that? Yeah, I mean, they have the event name and the event roster. That's the major thing. You send that out. Oh, yeah. Yeah. Okay. I'll probably do that just at the beginning, the morning of the meet. Okay. Oh, gotcha. So we just update the new list, or you will, yeah. All right, cool. All right, thank you. Bye. All right, so chromatography basically separates it based on, hey, is it polar or not? It's really the bottom line here. Okay, so let's move on fast. All right, so chromatography here, it's going to take advantage of, aka, of the intermolecular attractions. Right, we have the dispersion forces, which doesn't really help us out, but then we have dipole, which is polar bonds you have to have, or we have hydrogen bonds, which are even stronger version of dipole versions. Now, we talk about mobile and stationary phase, essentially mobile moving, and you'll see that on the diagram here that we're going to show up. Questions? All right, so here we go. Pictures tell 1,000 words here. So chromatography, you have a solution. Again, solution contains multiple parts. That's represented, it says ink spot, and this is actually kind of a cool, like, second grade experiment that you can do. If you took a marker, like the Crayola markers, and you cut up like a coffee filter, you can do this experiment. You just soak it in water, and you see the different colors that thing or marker is made out of, okay? So you put it in the solvent, okay, and you have to identify what the solvent is. If we're using water, water is really, really polar. So if these things get sucked up via water, that means that part of the solution was very, very polar, okay? We can use other things that are non-polar, like hexane. Wouldn't suggest putting your face over hexane, but you could use it. It's a non-polar substance, and that's because it would suck things up differently. So in hexane, if it sucked it up, it's a non-polar substance. Remember from solutions, and this has been way back ago, likes attract likes, okay? Now, what happens is this, right? And a marker is a perfect example. Particularly different color markers, they are composed. I'm sure Mr. Casson could explain more about the colors and art stuff and that, but they're composed of different colors to produce that particular color that we see. We separate them out based on their differences in polarity. Okay? Questions? All right, well, so let's try an example. So this is a multiple choice question here. We'll go over the answer just like I did yesterday. I printed out all the answers, so you have the book by book definition of what an AP chemistry problem would look like in this particular topic. It says in paper chromatography, a sample of pigment is separated into two components, X and Y. The surface of the paper is moderately polar. What can be concluded about X and Y based on the experimental results? So it is polar. So if we have component X, it's higher after the experiment gets done. It's higher on that strip of chromatography paper. So based on that, is X more polar or not as polar as Y? Is it more polar? Okay. So on yeah. So. Oh, I'm not identifying something correctly. Hexane, I just got done talking about this, is a non-polar solvent. Okay, so this means, and I had things backwards here, that if X is higher, it is more non-polar. So that means Y is what? More polar, and that's your correct answer, D. Y is more polar, all because it's wanting you to identify hexane. Now we know we haven't talked about this, but again, you don't see any hydrogen bonds. You don't see any polar substances because it's a carbon ring circle. So it's a non-polar. The higher something is, the more non-polar, the more like it is like the salt. Does that make sense? Okay. All right, so example problem number 2. This would be like a free response, probably a short free response. It says student obtains a sample of purple food dye, which is known to contain both red and blue dyes. It's dissolved in a solution of isopropyl alcohol. Sketch an appropriate lab setup in order for the student to separate the two types of dyes. Then it goes on to say, if the blue dye is less polar than the red dye, which would we expect to travel furthest on the non-polar stationary paper? Okay, so we have quite a bit of things going on, right? Number 1, your basic setup would be this. We have a cup, and inside our cup, we would have our solvent, which is isopropyl alcohol. Okay, so we'll call alcohol. Oh, forgot my O. Then we would have our chromatography paper, and essentially it would be set into our alcohol, and then we would put a little ink dot there, all right, which it says it's purple. So I'm going to put that purple dot right there. It'd actually be submerged below, or it could be submerged above the alcohol level, but that's just basic lab setup. And then we have this. It says, and this is important, that Blue dye is less polar than red dye. Okay. So if blue dye is less polar than red dye, alcohol, do you predict it to be a polar or non-polar solvent? It's polar because of that OH, that hydroxyl. Because of that OH hydroxyl group. Okay, that's a really polar part of it. All right. So red is more polar. Red is more polar. Does red go higher on our sheet or lower on our sheet? Higher because it's polar. So our red dot here, you would have your red dot. I'll call that the red dye or whatever you'd want to call it there. And then you'd have your blue dot, which wouldn't be as high. Okay. Now, again, I'm going to give you the textbook definition, but not only do they want to see you draw a picture and put things in the correct order, one thing they probably did me for is that, oh no, that little purple dot should be above the solvent line. In the explanation, here's the, again, textbook definition. Since the solvent, the mobile phase, is slightly polar, the blue dye will be less attracted to it and more attracted to the paper. The red dye is more polar and will be more attracted to the solvent than the paper. This makes the red dye travel further. Okay? Questions? Anybody need this? I'm going to give you the textbook answers here in the notes, and we'll keep going. All right? Now, distillation, this is a really common organic technique because you put a bunch of organic chemicals and then you basically boil them out based on their differences in boiling points. Again, distillation, same thing you've thought of before in distillation. You have this mixture here in this little glass bowl there, round bottom flask is what it's called. And then you have a distillation tube and you would hook it into cold water so it cools it down. So what we do is we heat it up, and at that time, one portion of your substance boils, and then it gets in that tube, you cool it down so it condenses back, and you collect just that sample, okay? It's all based on, difference in intermolecular forces, but really differences in boiling points of each liquid, okay? Alcohol is going to boil at a different temperature than water. You can separate them out. Any questions? All right, with distillation, again, major thing, different intermolecular attractions. Water, well, let's do water and oil. Okay, that's an easy example. Obviously, they'd separate out, but if they mix together for whatever reason, you would have stronger intermolecular forces with water compared to that of oil. You could boil those out because they would have different boiling points, all because they have different intermolecular attractions. Okay, questions? All right. All right, so we look at the structure here. It says a mixture containing equal number of moles of ethyl acetate and butyl acetate was separated using distillation. Based on the diagram shown above, which of the following identifies a substance that would be initially present at higher concentration? What that is trying to tell you or trying to get you to do is, okay, which one would have the lower boiling point and then why? Okay, so we look at both of these things. Both of them look very, very similar in terms of what they're structured. However, there's one key difference. Anybody know what the key difference is? How many carbons are over here on the left? 4. How many carbons are over here on the right? Okay, bigger. All right. Do bigger things typically move faster or slower? Slower. That means they're going to boil at a higher temperature because you got to get their energy going. All right. So in our solution, the first thing that's going to boil off is this ethyl acetate because it's a little bit lighter. All right. It has less intermolecular attractions, less dispersion forces because it's smaller. All right. So the correct answer on this particular problem would be B, ethyl acetate, because it has shorter carbon chain, aka lighter, and weaker dispersion forces. Now, what it's trying to get you to identify is this. Both of these substances are nonpolar. How I can tell that? There's no hydrogen bonds. There is no polar portions of this particular molecule. And there's a really long carbon chain. 2 or 3 carbon chains start to get connected together. Typically, you're going to have a nonpolar substance. Again, correct answer B. Questions? Anybody need this? Now, is everyone okay if I just go over verbally this problem? Okay. This would be a free response. You're going to get the textbook answers here in just a moment. But it says here, a student observes that a mixture of butanol, the OL means there's an alcohol group, a hydroxyl, an OH group attached to that, and pentanol, they're miscible, which means they do what if we put them together? Mix. They mix. You couldn't tell them apart. Again, back to that coffee and cream example. Using our information in the table above, what technique could the student use to separate the 2 components of the answer? All right, or of the mixtures. What is it? Distillation. Yes, because we just got done talking about distillation. Yes. Very good. The key to this is that they are mixed together. And the other key is that they have different boiling points. Because they have different boiling points, pentanol has stronger intermolecular forces because pentanol is bigger. Okay? Again, bigger, takes longer to get moving, more energy required, higher temperatures to boil this. All right? Lower, again, key points, you identify distillation. The other key point, butanol would boil off or vaporize faster than pentanol because of the differences in intermolecular forces and that boiling temperature that's C. That would be your justification. Any questions? Okay, again, you're going to get those examples here. Spectroscopy in the electromagnetic spectrum. Okay, spectroscopy, we've already started to talk about spectroscopy. It's basically taking a specific wavelength. You're going to shine light into a specific object or concentration or solution, and you're going to get an absorbance/transmittance value. Okay? We kind of backtrack even more here, and this is the stuff I just really bulldoze right through. It talks about radiation. Now, Mr. Dorfler gets into this. I think it was chapter 6 he went over, but he got into this without probably calling it spectroscopy. So, electromagnetic radiation. Hey, everything around us that is light is going to be considered electromagnetic radiation. We have everything here from radio waves all the way over to gamma rays. And as you can see, as we move left to right in this picture here, we have increase in energy. And notice that our wavelength decreases and our energy increases. And then if we move backwards, wavelength really big, but our energy in that wavelength really small. Okay, this is important. Like when we were talking about the electron and things of that nature, this is kind of where it gets its root here. So we get to this point here with absorption and emission of photons, which we have to get into the photoelectric effect, which is really our next phase here. The higher energy a light wave has, the higher energy of photon it can inject, which we'll get into again with the photoelectric effect. So let's go over some of these basic problems that would be involved here. So the diagram above represents the absorption spectrum for a pure molecular substance. Which of the following correctly identifies the type of transition observed for the substance in each of these regions? Okay. Oh, so what it is doing, it's trying to get you to correlate this. Each of these levels or each of these variants of electromagnetic radiation is correlated to particular types of movement. And remember in our second part of thermochem, when I said, hey, degrees of freedom, and I said this particle would only have 1 degree of freedom, and we talked about Boltzmann equation and all that jazz. This is kind of an extension of that. Based on type of radiation, there's an energy associated with it, which means there is a type of movement that can be associated with it at that particle level, at that atomic level, and even the subatomic level. Okay. So what it's trying to get you to do is, okay, in the UV section, well, what particular in region X, in that UV section, if we look back, UV is associated with electronic energy, okay? And then you just keep pairing these together. And so what would happen, region X, again, because of that UV radiation, you have the spike there, you'd have that electronic transition. I'm pointing at D because it's the right answer. Region Y is that infrared, molecular, and so that's what that chart has you do there. And then your region Z would be microwave radiation. Okay. Questions? Notes. Didn't really do this one here. All right, now nitrogen versus iodine. Nitrogen, it says absorbs UV light, but not visible light. Iodine absorbs both of these things. Anybody have an idea why that would be? That's all right. We'll go over these a little bit more, especially when we do our review. But essentially, what happens is this. If we look at nitrogen versus iodine, which one is heavier? Iodine is much, much, much more heavier, which means, again, we just talked about that, a heavier item is going to take a lot more energy to get going. So this is saying nitrogen, okay, it absorbs UV light. So it's not enough energy to push nitrogen and get it going. But when we get to visible light, which if you're paying attention, the visible light was further to the right, which means higher energy. And so once we get to that visible light, it's like pushing off the cliff, and it shoots off and it gets higher energy. Iodine with visible light, again, it's a big boy. We can't push it off the cliff with that type of energy. Does that make sense? The notes go into more detail here about talking about the different types of energy, but essentially think mass here, right? Think mass related to energy. Questions? All right, let's get to the photoelectric effect. And so we have this photoelectric effect. Number one, Einstein did a lot of his research and things like that on this. Number two, we have two equations that can be interrelated together. This one, anybody know what C stands for? Yeah, speed of light is equal to our wavelength, that's your cool looking Y, times your frequency, cool looking V. Now, Planck said, hey, remember that we can eject an electron and there's some energy associated with that? The specific energy is equal to Planck's constant times our frequency. So if we can get our frequency from our light, we can figure out how much energy did that light have, and potentially how much energy does it take this electron to get ejected or really excited, okay? Cool, so this is how this works, and this is how we kind of interpret this, all right? In our spectrometers, which we've used a version of this with a calorimeter, light source, specific light wave, then our sample. Then what happens is the sample either absorbs or transmits so much light, and we read it as percent transmittance or absorbance. Oh, and then it talks about absorption really well. I wish I would have put this earlier. Absorption, right? Yeah, hey, it gets that energy, but it doesn't go off and do anything. Whereas emission, we get that energy and we get ejected out of it, right? That's what that little squiggly line to the right is trying to emphasize. Questions? All right, speed of light. We're going to use, I know there's a couple different versions. Physics, you probably use a more detailed C, speed of light. You might use 3 times 10 to the 8th. Or for us, remember, we're dealing with really small waves. We might use that nanometers per second. Then our energy of our photon, our big thing here, and both of these things are in your AP Chem handout that we have. And so we have the energy of the photon is equal to Planck's constant times frequency. Planck's constant is always 6.626 times 10 to the negative 34. All right, so in both of these things, these are both calculations. It says the complete photoelectron spectrum of an element is given in the ground state and represented above. We want to calculate the wavelength in meters of electromagnetic radiation needed to remove an electron from the valence shell. And then it says, hint, the valence shell has the least binding energy. So is it going to be furthest to the left or furthest to the right in this particular experiment? Which one's smaller?
Smaller.
What?
Like now, right.
Yeah. See how it's 0.98? They're all to the negative 18th power. Okay. Now, what it wants you to do, if everyone's good, you want to call this a good stopping point for the day? Then we'll finish it out tomorrow. All right, let's get through this problem and then let's go and deal with that. My voice is about ready to go here. This right here is the least binding energy. Okay? Oh no. Okay? Now, we have energy, and we have two formulas. We have E equals, wrong one. E equals Planck's constant times frequency. And then we also have, I'm going to write it over here, our speed of light equals wavelength times our frequency. And so in this problem here, we already know our E for energy. It's this guy right here. And that would be in units of joules. That's the correct unit. And so I'm going to start my problem. I'm going to say, all right, I got 0.980 times 10 to the negative 18 joules equals Planck's constant, which is 6.626 times 10 to the negative 34th joules seconds. And then you have times your frequency. Okay? So now how do I solve for my frequency? Divide by that Planck's constant. And let me see if I can pull my calculator out here. So I'm going to take 0.980 times 10 to the negative 18th divided by 6.626 times 10 to the negative 34. And my frequency to 3 sig figs is 1.48 times 10 to the 15th. I'm going to ask you what our unit is. 1.48 times 10 to the 15th. Seconds, not squared, inverse seconds. S to the minus 1. 1 over S. Okay? Well, hey, we know speed of light. Speed of light is what? Very good. Speed of light is 3 times 10 to the 8 meters per second equals our wavelength, which we don't know yet, times what we just found in our frequency. 1.48 times 10 to the negative, or excuse me, to the positive 15th inverse seconds. And so I ask you this, how do I get wavelength itself? Oh. So I take 3 times 10 to the 8th divided by 1.48 times 10 to the 15th, and I get a value of a lot of decimals, which I don't want. 3, I guess they went down to 2 sig figs because of 3.0. So your answer here for our wavelength would be 2.0 times 10 to the negative 7th. And what would our unit for length be here? Okay, good. All right, let's call that good, and let's do this. We will pick up and finish this tomorrow, kind of ease into spring break. We'll do the day 5 when we come back from spring break, which means this.